This week we've seen a lot of the theory behind loading and storing instructions in MIPS and how we must align things and we need to worry about which version of loading and storing instructions we're using. But today I'd just like to show you in practice how you might use some of these commands to manipulate words and bits. So you can see here that I've got the word A, I've given it 0, 1, 2, 3, 4, 5, 6, 7, 8 as a value. I've loaded it into T0. This should be all relatively familiar to you. But what I want to show you how to do is how to manipulate the different parts of this. So I'm going to say, let's store this word so we're going to need to give it the register that's stored at, and let's say that it's stored at there. So now I have the physical memory address that I'm going to access when I run this code. So what can I do? Well, let's say that I want to pull out all of the individual bytes. Well, I'm going to use load byte unsigned, and I'm going to store this in T1. Now, what I can do is I can say A, or equivalently, I could say x0, 1, or like that. A will already have been stored at this space, but you can force it to be stored there by using the store word command. So what this is going to do is it's going to pull out the least significant bit from the word, but because we're giving it an actual address, there is only 1 byte stored there. Remember, each register only, or each memory address only stores 1 byte. So we're just going to pull out the only byte that's there, and we're going to store it into a register. Now, equivalently, if I wanted to get the next byte in this word, and let's say I want to store that at T2, what I could do is I could say 0, 1, like that, because that's the next register up, or the next address up. And we know that each register stores a byte, and we know from the little endian architecture we go from least significant up to the most significant. So this is just going to pull out the next byte. So let's run that and see that that works. And yeah, so you can see here we've got 7, 8 and we've got 5, 6. So we're happy. Now, equivalently, I could do this, which would get me the same result. So let's store it in T3 just so that it's easier for us to compare. I could do A plus 1, because A is a label giving me the memory address where this is stored. So A is equivalent to this thing here, but if I do A plus 1, I'll also get the same result out. So let's play that. So there you go, I've got 5, 6, 5, 6. So these are two different ways that we could access the bytes. And if we wanted to, we could continue to increment. We could go 102 and 103, and we could get each of the individual bytes out. But what I'd like to show you now is how to manipulate some half words. So let's say you were set a problem. Someone says to you, here's a word. What I want you to do is take the half words out and swap them around and then store that somewhere. So how would we do that? Well, we'd need to start loading half words. So let's load half word unsigned. We're going to store it in T4 so we don't overwrite anything that we've used. And we're going to say 0x 100 10000, and that should give me the first half word. Equivalently, I'm going to take out the second half word. This is going to be the most significant bytes, and I'm going to store them in, oh no, I'm not going to store them. I'm going to take them out from the second place, so that's going to go above the least significant and take out the most significant. Now, a trick I'd like to show you in this video is how you reserve space and memory, or just give space and memory a label. There's a few ways we could do this exercise, but I want to show you a specific way just so that we know how to do that in the future. And what we're going to say is B is going to be our new address where we're going to store this reversed word, and we're going to call this, and we're going to give this the type dot space. I'm going to say 4. Now what dot space does is it gives a certain amount of memory, a number of bytes that you specify, in this case 4, a label, and we're giving it B. So we're saying B is some memory address that's got 4 bytes worth of storage there, and that's all I need. So I'm going to reserve that now. So then what we want to do is store the half word, and we need to reverse it. So the most significant bits should be stored at the first part. So what we should do is we should take T5 and we should store them at B. And then what we should do is take the ones at T4, the least significant bits, and store them at B. Shit, I think this needs to be spaced at B plus 2, like that. And then what I'm going to do, just so that we can see it, is go to load words, into A0, let's say, and it's going to be B that's loaded in there, and we'll compile that and see what happens. So everything's fine. We run this, then we look over to A0, and you can see that's 5, 6, 7, 8, 1, 2, 3, 4, which is our original word but swapped around. So that's how you would do this using Mars. Again, you don't have to do it this way. You could just specify an address, so equivalently to how we saw these are two equivalent things, we could have just written something like 0x100123 because I know that that's a valid memory address, and I could have compiled that and ran that had I been so inclined. We can see that happening here, and yeah, 104 has some stuff stored in it. In fact, that's the label that B has been given, so this is overwritten here. But yeah, there's different ways to do this. I just want to give you a feel for some of the options you have when you're manipulating memory and how you might swap things around, that sort of thing.